3D visual grounding aims to locate objects mentioned in natural language descriptions within a 3D point cloud scene, which is a promising 3D vision and language cross-modal research. This work proposes a new and challenging setting, grounding objects without mentioning their names. The model needs to have a holistic understanding of the visual and language context to make inferences, avoiding shortcuts based on object names. We contribute to introducing a text decoupling and dense alignment approach to avoid imbalanced and ambiguous learning. We also propose a novel 3D VG task to evaluate the robustness of the model. Finally, we achieve state-of-the-art performance on the standard 3D VG task and absolute leadership in the new setting. In this work, we focus on 3D visual grounding, which aims to find the object mentioned in a language description within a 3D point cloud scene. For example, there are 3 descriptions that locate different instances of the same category, the trash can. This task requires a comprehensive understanding of object categories, appearance attributes, spatial relationships, and other cues at both visual and linguistic levels. However, we observe 2 limitations in existing methods. One is the imbalance in feature learning. For instance, in the given language description of, "This is a brown cabinet. It is next to the green-blue curtain," there is only one instance of the cabinet in the scene. The model tends to rely heavily on object categories for inference, thereby taking shortcuts and neglecting the learning of appearance attributes and spatial relationships. Another example is the word trash can in the previous instance, which can significantly filter out most of the candidates. We refer to this as the inductive bias brought by object categories, where the dominance of object category names in the feature learning process weakens the learning of other attributes, resulting in imbalanced learning. Another observation is the ambiguity in cross-modal feature matching. A common approach is to match sentence-level features with individual target objects. However, a sentence often contains multiple semantic cues, some of which may match the target object, while others may not describe it. This sentence-level and coupled features can lead to ambiguity in the visual textual matching process. Our insight is text decoupling and dense alignment. Firstly, the input text description is decoupled into multiple semantic components by grammar parsing tools, including attribute, main object, relationship, pronoun, and auxiliary object. Then, the text components relevant to the target object are densely aligned with visual features to avoid feature learning imbalance. Finally, different text components are explicitly associated with specific objects to avoid ambiguity in multimodal feature matching. This is our framework, which can be divided into 3 modules. The first module is text decoupling. We decouple a text description into 5 semantic components. In this example, the main object is chair, with attributes such as brown, armrests, and legs. The blackboard is the auxiliary object, and their relationship is under. Then, based on the position of the text, we obtain binary position labels for each component. Finally, we extract decoupled text features based on these labels. The second module is the extraction and fusion of multimodal features. For text descriptions, we first preprocess them using Roberta and then extract text features using a transformer-based language encoder. For 3D point clouds, we tokenize them using a small PointNet++ and then extract point cloud features using a visual encoder. Additionally, there is modulation and fusion between text and visual features. Finally, the decoder selects 256 candidate objects from the point cloud. The final module is the dense alignment loss, which supervises multimodal feature matching. We propose 2 losses, position alignment and semantic alignment loss. Taking the latter as an example, we aim to maximize the similarity between the visual features of the target object and its corresponding text component features. In the end, out of the 256 candidate objects, the one with the highest similarity is considered as the model's prediction. In the experimental section, we first compare our method with state-of-the-art methods on the ScannerFir and SR3D and R3D datasets. Our method achieves the best performance on almost all metrics, even surpassing methods that use 2D image assistance for 3D point clouds, when using only 3D data. More importantly, we introduce a new subtask, grounding without object name. We replace the object category in the text description with the term object, forcing the model to understand the text based on context rather than relying on object names as a shortcut. The results show that our performance far surpasses other methods, demonstrating the robustness of our model. Next, we conduct ablation analyses to demonstrate the contribution of each text component and each loss to the performance. Following, we present some qualitative analysis. The first line represents the ground truth, and the second line displays our model's results. These examples demonstrate our model's understanding of appearance attributes. These particular examples showcase our model's strong comprehension of spatial relationships. Surprisingly, our method even accurately understands ordinal numbers. Lastly, we provide results of our method in the novel setting of not mentioning object names. In summary, we address two critical challenges in this domain: the imbalance in feature learning and the ambiguity in multimodal feature matching. We propose a text decoupling and dense alignment solution to tackle these challenges. Additionally, we propose a novel and challenging subtask of grounding without the object name, which enables a comprehensive evaluation of model robustness. Thank you for your attention.